Hello everyone, this is Abhinav. Today we'll be discussing the 18th problem from the CP-31 sheet by TLE Eliminators under the 1500 rated problems. Let's begin. We'll move on to our CP-31 sheet and we can see the 1500 rating mark has been checked. Let's move on to the 18th problem, which is Ehab and the Path-etic MEXs. Okay, so let's read the problem statement. You are given a tree consisting of n nodes. You want to write some labels on the tree's edges such that the following conditions hold. A label is an integer between 0 and n minus 2 inclusive. All the written labels are distinct. So if we read the first two conditions, what we can conclude from that is a tree has, if it has n nodes, it would have n minus 1 edges. I hope you know that. So after that, you need to assign labels from 0 to n minus 2. That means from 0 to n minus 2 in this range, a total of n minus 1 integers are there and all the labels has to be distinct. So basically for the n minus 1 edges, you have to assign these n minus 1 distinct integers. Every edge would have a different label. So one integer would be assigned to any one of the edge. Now, the largest value among MEX UV over all pairs of nodes UV is as small as possible. What does that mean? Is here MEX UV denotes the smallest non-negative integer that isn't written on any edge on the unique simple path from node U to node V. So if we take any two nodes U and V, so we know in a tree there would always be a simple path from a node U to node V, and that simple path is always unique. So that unique simple path from node U to node V, in that path there would be many edges. So among those edges, whatever number is written on that edge according to the first two conditions, the number that we assigned, the label that we assigned to that edge. So if we take the sequence of those labels, whatever is the max of them is actually the smallest non-negative integer which is not present. Let's say we have 0, 2 and 5. So minimum number which is not present, 0 is present, 1 is not present. Okay, so I'll explain those things from an example. So I hope if you know what max is, okay, that it is. Now what this condition states is the largest value among MEX UV over all pairs of node UV is as small as possible. That means if you consider any pair, if you consider all the possible pairs of UV that you can have in the graph, then for every pair, if you calculate MEX of UV, whichever is the largest value among all those pairs, you need to keep that value as small as possible. So you need to have such an assignment so that this value is minimized. You need to minimize the largest possible value of MEX of any of the two nodes. That's what you need to do. So the constraints are n is up to 10 to the power 5 and you are given a tree. So all the information about the edges of the tree. Okay, so let's look at the first test case to understand what we actually need to do. Okay, or maybe let's look at the second test case. You will be able to understand more clearly from the second test case. And I think the tree from the second test case is given to us. So we'll just take that tree that side. Okay, so if we look at this second test case, so this is the tree given to us. So the node, this is in the form of test case, the tree that we get. There's an edge from 1 to 2. So from 1 to 2 there is an edge, from 1 to 3 there is an edge, from 2 to 4 there is an edge, from 2 to 5 there is an edge, and from 5 to 6 there is an edge. So information about these edges are given and n is 6, so there are 6 nodes. That's what is given to us. Just ignore these, what I can say, the labels that are written here. So for now this is our problem. Okay, these labels are currently not there. So now we need to assign labels to these edges so that, so n is 6, that means the labels would be from 0 to n minus 2. So from 0 to 4, in total there are 5 labels from 0 to 4. We need to assign 5 different labels to these 5 edges. Okay, so we have 5 edges, we need to assign 5 different labels from 0 to 4 to these 5 edges. So after the assignment of those labels, whatever is the value of this that we get, the largest value of MEX UV over all pairs of UV, you need to minimize that. So the assignment should be such so that this value is minimized. So let's like randomly assign any one possible assignment and try to calculate the value. Okay, let's say you assign 0 here, 1 here, 5 here, 4 here. So you need to assign from 0 to 4. So 5 is not present. 0, 1, then 2, 3, 4. Okay, let's say this is the assignment. This can be one possible assignment. Let's try to calculate the value of this, the largest value of MEX UV over all pairs of UV. So what would be the all pairs of UV that may exist? So if you take U as node 1, then from 1 to 2 that is one path, from 1 to 3 that is one path, 1 to 5, 1 to 4, 1 to 6, these all would be the paths from 1. Then same from 2, these paths would be there. So if you look at all the paths, which is the in any of the path the largest MEX. So if you consider any one of the paths, let's consider if I'm taking UV as 5 comma 3. So from 5 to 3, this is the path. So for this path, the values we are having is 2, 0, 2 and 3. So for this particular path, which is the smallest value not present, it's 1. 1 is not present here. So for 5 comma 3, the MEX of 5 comma 3 we can say would be 1. Okay, if you consider MEX, let's say any other UV, let's say from 6 to 3 if you are considering. Okay, from 6 to 3, what would be the MEX of that? So in this path we have 1, we have 0, we have 2, we have 3. So 0, 1, 2, 3, these are present. So which is the smallest value not present? 0 is present, 1 is present, 2 is present, 3 is present. Smallest value not present would be 4 here in this case. So in this path we can see the MEX we are getting is 4. If you take any other path, okay, whatever, let's say 4 comma 3 if you are taking, so in this path you will have 4, 2 and 3. So 0 is not present, so directly your MEX would be 0. So in whichever path 0 is not present, this path, this path, this path, this path, this path, for all those paths your MEX would be 0 anyways. For this path you have 1, 0 and 4, so MEX would be 2 here. For this path it was 0 already. For this longest path you had MEX of 4. So which is if you consider all possible UV, which is the largest MEX you are getting is 4. You are never getting more than 4. So more than 4 what you can have is 5. So in order to have 5 you should have all numbers from 0, 1, 2, 3, 4. So in this particular assignment, can you have all numbers from 0, 0, 1, 2, 3, 4, all those in a single path? I think no, because you cannot have all the edges. You don't have any two nodes in whose path all the edges are coming. So this 5 is not coming here. So the maximum value actually in this assignment is 4. So for one particular assignment, I hope you got how we are calculating the largest MEX value. Now you need to have this assignment such so that this final MEX value is as low as possible. Here you had a MEX of 4. So you need to basically minimize this value. So let's try some different assignment. Okay, so let's look at the assignment which was given to it, which was having the minimum value. It's this assignment. It is having 4, 0, 2, 3, 1. So for this assignment, let's try to calculate our MEX. So if you, let's say this longest path, here you have 1, 4, 0 and 3. So you have 1 and 0, you don't have a 2. So for this path, MEX of 6 to 3, your value is 2. Okay, 2 is not present in this path. Okay, if you take this path, here 2, 0, 3 are present, 1 is not present. So in this path you can say that MEX of 4 to 3, in this path 1 is not present. If you take this path, here 0 is not present. Okay, so these smaller paths would obviously be less only. Okay, so any possible path if you take, the maximum value you are getting here is 2. You can try on this particular assignment, you would never get a value more than 2. So more than 2 you may have 3. So to have 3 you should have 0, 1 and 2, all of these together in a path. So you have 1 here, 0 here, 2 here. Whatever path you take, either you may have like this or like this or like this. You would never have a single path containing all these three numbers. That's why you would never get a, so you would always get a MEX as 0, 1 or 2. In any path, at least one of them is missing. So the maximum you are getting here is 2. So from this test case, you can see the for this particular assignment, your maximum MEX value is 2, and that is the minimum you can get. So for any assignment, you can never reduce the maximum to less than 2. So your answer for this test case was 2. You can see the answer for this test case, like 2 is the minimum of the largest MEX you can get. The answer is actually the whole assignment. You have to answer all the assignment. So for the first edge from 1 to 2, from 1 to 2 you are assigning, where is 1 here, 1 to 2 you are assigning this as 0. From 1 to 3 this edge is assigned as 3, so this is assigned 3. From 2 to 4 this edge is assigned 4. From 2 to 5, 2 to 2 to 4 is assigned 2, 2 to 5 is assigned 4. Okay, 2 to 4 is assigned 2, 2 to 5 is assigned 4, and 5 to 6 this is assigned 1. So in the order of the given input, I have to answer in my output also. So 0, 3, 2, 4, 1 was my assignment, 0, 3, 2, 4. Okay, so I hope you understood the problem, what we need to do after understanding this test case. Now, how do we solve this problem? That's the problem. So let's look at the constraint first. So the constraint given to us is n is up till 10 to the power 5. So n less than equal to 10 to the power 5. So looking at the constraint, what we can conclude is our solution should have a time complexity of probably order of n would be all right. Order of n log n, that would also be all right. Even we can go up till n root n, that would be all right. But if we go to something like n square, that would have 10 to the power 10 a total of operations, that would exceed our time limit, because in 1 second we can have only 10 to the power 8 operations. So we can say that our these are our possible expected time complexities in which we need to solve the problem. So basically we have to be linear, or maybe we can have some log factor extra, but basically we have to be linear. N root n is a very rare case, and in this tree type of problem that would not occur most probably. Okay, so now we need to find some linear solution to this problem. So how do we do that? So let's try to analyze this problem first. So how do we minimize our largest mix? So if we just take any random tree, okay, let's say we have any random tree. Okay, something like that. Now, whatever tree you take, so in this random tree, there would be some edges, okay, and every edge would be labeled differently from 0 to n minus 2. In that range, you label every edge. So what would be our final, the value that we need to minimize? The largest max. So the largest, for the largest max, first thing is, if you just consider one edge, one edge, one edge, that is like very rare case. So whenever so a better case to consider would be like some large paths, then only our max can be increased, or then only we would get the largest max, because you have to consider all possible UV. Okay, so if you consider any of the paths, then in that path what you need to make sure is, let's say I'm telling my answer is the largest value is, let's say, 4. Okay, we need to minimize this largest value. So if you want, let's say there is one possible assignment which is fetching you a largest value of 4. If you want to change that assignment and minimize it to 3, then what would you need to do? Okay, so if you want to have your answer as 3, what I'm asking is, if you want to have your answer as 3, what is the condition that this tree should satisfy so that your answer is 3? It is that in any of the path it should not have a value greater than 3. Any of the paths should not have a max greater than 3. When would the max be greater than 3? If you try to think, the max would be greater than 3 only if in a path you have 0, 1, 2, 3. If you have all of these, then the max would become 4, or if you have 4 also, it would become 5. So it can become greater than 3 only if you have all values from 0 to 3. If any path you take, then if the tree is something like where whatever path you take, either 1 is missing, sometimes 3 is missing, sometimes 0 is missing, it's not possible that in that tree you can have a path containing all the 4 of them. Then your answer would be 3, because then in that case you can never have a max greater than 3. So in order to reduce your answer to 3, you need to make this assignment such so that whatever path you take, you can never have all the values from 0 to 3. Okay, that thing we know. Now how do we do that? So if you just look at this sample test case only, just looking at the answer for that, maybe you can get some idea that here we were able to reduce our answer to 2. So how do we did that? In order to reduce your answer to 2, you need to make sure that 0, 1, 2, these three integers are not occurring in a single path. How do we make sure that? We have 0 here, 1 here, 2 here. If you look closely, when would be the case when you have all these three together in a path? So here you can see, if you have a path from 1 to 2, in order to move to 2 you would turn here, so then you would never return back to 0. If you have a path containing 2 and 0, then it would be something like that, you won't go to 1 from here. If you have a path containing 0 and 1, it would be something like that, you won't go to 2 here. So if you look closely, this particular edge, this particular node 2 is actually dividing these three numbers, three labels, 0, 1 and 2. These three labels are actually in three different subtrees of this node 2. So if that is the case, then there won't be any, you would never have a path containing all the three of them. What I'm saying is, if you, whatever tree you have, if you have any one node, let's say add something like that. If you look at this root node, whatever root node you have, that root in any general tree, let's say that root node has three children, three or more children. So if you assign 0 in one of the subchild, 1 in another subchild, and 2 in a different subchild, then if you, it has three different subtrees, okay, not subchild, subtrees. Okay, so in this subtree somewhere you keep 0. In this subtree, okay, this is the a different subtree of this root node. So in this particular subtree somewhere you keep 1, and in this particular subtree somewhere you keep 2. If you do that, then you would never have a path containing all the three. If you try to have 0 and 1 together, you would not have 2. If you try to have 1 and 2 together, you would not have 0. If you try to have 0 and 2 together, you would not have 1. So from this we can say that we can always, or I'll pause on the always part, but in a general tree we can see that we can actually make this happen, that you would have 0, 1, 2 in three different subtrees of one particular node, and then none of 0. So you can reduce your MEX to 2 in this case. So you would not have, you would never have a MEX value of 3, because in order to have a MEX value of 3, all the 3 should come. So here your largest MEX is reduced to 2. So here I was talking about 3, but you can actually reduce it to 2. The only condition here is, in order to reduce it to 2, you should have one such node which has 3 children. If you have a tree where there are all nodes, something like a pipe, okay, so if you have a tree which is a pipe, if I am telling, where it's just like a chain, it's a single chain, there are no sub branches to any of the nodes, then in this particular tree you would always have this path which is contains all the edges. Okay, you can never have a node which has 3 children so that you can assign 3 different numbers to all of them, so that none of the 3 numbers come together. That condition that we were trying to do here, that you cannot do in this type of tree. So this is one exception where you would have to compute differently. So what would you do in this case? So for this special type of tree, where which is a single line tree, or which is called a pipe, so in this tree there is this path which contains all the edges, and if it contains all the edges, it would have all the values from 0 to n minus 2. And if it has all values from 0 to n minus 2, whatever assignment you do for this particular path, you would always have MEX as n minus 1, because it has values from 0 to n minus 2, all the values from 0 to n minus 2. So for this case, always your answer would be n minus 1, whatever assignment you do. So for this type of tree, we would just randomly assign 1, 2, or we can say we'll just randomly assign each as 0, 1, 2, 3, because it doesn't matter whatever assignment we give, it would fetch the same largest max value. So in this case, you actually cannot minimize it. That is only the minimum, whatever assignment you do. So for this type of tree, we'll just do any assignment. And if you don't have this type of tree, then what we can do, we can always reduce our answer to 2. Now, can we reduce it to less than 2? First, let's try to do that. If we can't, then yeah, this is the best answer. But can we reduce it to 1? When would we have a MEX of 1? If we have a MEX of 1, that means, like, the largest MEX of 1, that means you can have MEX of 0 and 1 only. You never have a MEX of 2. So you don't have a MEX of 2, that means to have MEX of 2, you should have 0 and 1 in a single path. So is it possible that you have a tree where whatever path you take, in none of the path 0 and 1 come together? That is actually, if you try to think, not possible, because wherever you have 0, okay, let's say there is some random edge which has 0 and there is some random edge which has 1. So whatever two edges you take, if they are in different subtrees, then whichever is the node just above that edge, there would be a simple path between these two nodes. And if there is a simple path between these two nodes, then if we consider these two nodes, then in this simple path both 0 and 1 would come. And if it is the case where in here you have 1, here you have 0, then obviously in this path only both of them would come. So if one is below the subtree of other, then it would definitely come. If they are in different subtrees, still there would always exist a unique simple path between any two nodes in a tree, because all the any two nodes in a tree are connected. So this simple path would always exist, which would have a MEX value of 2. So actually you can never reduce the MEX to less than 2, unless obviously if you have only one edge, if it's n equal to 2 case. That's the only exception for that you can say is, if you have only one edge, that would have a label of 0 only, and it would have a max of 1 only. In that case your answer would be 1. But for any other case, whenever you have n greater than, whenever, I'll write it more cleanly. So for n equal to 2 case, you would have this graph only. There are two edge nodes which are connected. So in that, obviously that one single edge would get a value of 0. That's your only option available to you, and it would have a MEX value of 1. So like if you just exclude this n equal to 2 case, then for any tree having more than 3 edges, even if you have 3 nodes, more than 3 nodes, then you would have at least 2 edges, and those 2 edges would be assigned 0 or 1. So if you have more, at least n greater than equal to 3, there are at least 2 edges, so there would be 0 and 1 present there. That means your MEX has to be greater than equal to 2. So if your MEX is greater than equal to 2, then there are only 2 cases. If it is a if it is a pipe, then you cannot reduce it to 2. Your answer is n minus 1. Have it in any way, just do any assignment. And if this is not the case, then you can always reduce to 2, your MEX to 2. How do you do that? You need to just find any one edge, any one node which have a degree more than 2. So if you can find any one node having a degree more than 2, then what you can do? So if all the nodes have a degree less than equal to 2, then it is a pipe. What is the condition to not be a pipe? Is there is at least one node having degree at least 3. So if there is a node having degree at least 3, you can just assign 0, 1 and 2 to those 3, the edges adjacent to that node. So once you do that, then you have just reduced your MEX value to 2. For any path you take, you would never have your MEX value more than 2. Once that is done, the remaining assignment, the 3, 4, 5 can be done in just any random order. That's what you need to implement. Okay, I hope the logic is clear. So what you need to do for n equal to 2, just assign 0, leave it. Your answer is 1, no issues. But for n greater than equal to 3, just check if graph is a pipe. What does pipe means? It means if there exists any one node which has a degree more than 3. Okay, so if yes, it is a pipe, just do any assignment. It doesn't matter. For a pipe, whatever assignment you do, always it would fetch n minus 1. But if it is no, then if let's say x is a node having degree greater than equal to 3, then whatever node x is there, the edges adjacent to them, assign them 0, 1 and 2. The 3 different edges adjacent to node x, assign them 0, 1 and 2, and remaining edges anything. So for the remaining value from 3 to n minus 2, you can assign just any value to any edge from 3 to n minus 2. Okay, whichever are unassigned apart from these 3 edges, assign them anything. That's what you need to implement. I hope it is clear. So let's move to the code to understand how we are implementing it. Okay, so if we look at the code, first we take n as input, and then I'm taking the tree as an input in the form of an adjacency vector. So I have a vector of pair of ints. So why I'm having pair here is whenever you have a edge from u to v, I'll store in adjacency u, I'll push back v comma I, because in my final answer you can see I need to print the labels in the order of the input. So in the n minus 1 edges that I'm getting as input, I'm assigning them an index from 0 to n minus 1. So this I is an index from 0 to n minus 2. So I'm storing that the edge from u to v has an index I, edge from v to u also has an index I, because that's the same edge actually. So I'm assigning an index to that edge, so that finally while calculating my answer, I can assign that the answer of that index is what this edge from u to v should have, the label that it should have. Okay, so just for my answer, I am also keeping the index of the edge according to the input in my adjacency list. Okay, so once that is done, after that I have my answer vector which has indexes from 0 to n minus 2. Initially I have stored -1, that initially all those labels are unassigned. One by one I'll assign the label. So k is equal to 0, it means the next assignment I have to do is answer of 0, or you can say the next label that is unassigned is 0, because I have to assign all values from 0 to n minus 2. So I'll start with 0. First I'll check from 1 to n for all the nodes numbered from 1 to n. If there is any node having adjacency I dot size, that means the degree of that node, the number of edges it is adjacent to. If the degree of that node is greater than or equal to 3, that means it is not a pipe. If it is not a pipe, it is that case. So x is the node which has degree more than 3. So all the three nodes, three edges adjacent to node x, they would be assigned 0, 1 and 2. So uh, adjacent to I is the x here. So the node adjacent to I is adjacency I, stores the vector of edges adjacent to I. So I0 is the edge adjacent to the first edge adjacent to I, dot second would have the index value I. Okay, so at that particular index I'll say the label is 0, and same way for I1 and I2 they would have label 1 and 2. So the three adjacent edges to node x, they are assigned labels 0, 1 and 2. Okay, that thing is done. After that I'll update my k to 3, that 0, 1, 2, that is done. Now I have to, for the remaining assignment, I have to start from 3 and just randomly assign anything. So just break out. After that, if this if condition is satisfied one time, then we'll break out after satisfying it one time. If it is not satisfied any time, that means for all the values from 1 to n, there was no node having degree more than 3. That means it is a pipe. So for a pipe, k would remain 0. So in case of a pipe, k would remain 0. So I'll assign all the numbers. I can just assign randomly anything. So I'll just loop through from I equal to 0 to n minus 1, and whatever, if answer I is unassigned, it's still -1, I'll assign answer I as k and do k plus plus. So that 0 is assigned to first index, 1 is assigned to second, 3, 2 is assigned to third. That wise all the values are assigned if the k remains 0, and if the k becomes 3, then for these three values this statement would become false because answer is already assigned. For the remaining values, I'll keep assigning starting from 3. Starting from 3, rest of the values would be assigned in any order. Okay, so that is done. After that, I'll just print my answer. Okay, so I hope the logic and code, everything is clear about this problem. Okay, so if we analyze the time complexity, this input part I am having n minus 1 inputs, so order of n from here. Okay, and this is running n times, and this, under this if condition, all are order of 1 operations. So at max, if this break is not encountered, this would run n times at max. So order of n for this loop, and this would also run at max n times. Order of n for this would also run at max n times. Okay, so we can say our time complexity is order of n only, and our space complexity is, we have an adjacency list of size at max n. It has at max 2n pushbacks, so its size would be 2n at max. Okay, so our space complexity would be order of n only, and this answer vector is also having size n only, so it's order of n only. Okay, so I hope the time and space complexities are also clear. So this was a nice tree problem where you didn't have to do any DFS, BFS type of any traversal or any tree algorithm in this tree or graph algorithm. It was basically just logical understanding how a tree works and then analyzing the problem, getting the logic that, yeah, if we can always reduce the max to 2 if the tree is not a pipe. So understanding the property of the tree was the thing behind this problem. I hope you liked the explanation. Thank you very much for tuning in.